Well, hello again, and welcome to the NSS 2021 Virtual Convention. Today I'm going to be doing a presentation on batteries. Cave lights, the lights that we use in caving lights are quite important, and there are substantial differences in how they perform. I found particularly that the 18650 lithium-ion battery is very well, let's just say there's a lot of Chinese knockoffs out there. There's a lot of snake oil in that business. So the presentation that I'm going to run through today is a comparison of several different kinds of 18650 lithium-ion batteries and several kinds of nickel metal hydride AA and AAA batteries, and I threw in some dry cells just for comparison. One of the important things that I want to go over with in this presentation is the method that I used for creating the data. Basically, I used a Raspberry Pi with an analog to digital controller attached to it and some other controlling circuitry and a rather simple Python program to collect the data. And the data was then analyzed using a lab plot to produce graphs, and you will see quite a bit of those in this presentation. I think the place to start is to recognize that all batteries are not created equal. There's a lot of capacity variation among the batteries, and that's especially true for the 18650 lithium-ion batteries. I've looked all over Amazon trying to find good 18650 batteries, and they just don't exist on Amazon. I had to go to a specialty store called 18650batterystore.com to get any kind of decent 18650 lithium-ion batteries. Snake oil is probably the best term to use in describing the existing, the commonly available anyway, 18650 lithium-ion batteries. You can pretty much weigh one of those batteries. If it weighs less than about 45 grams, it's junk. Most 18650 batteries will weigh around 35 grams, and with those batteries, you know that the capacity is only 800 to 1000 milliamp hours. Sometimes not even that. So let me talk about the test rig a little bit. That's probably a very interesting thing for many of the people listening to this. I use an old Raspberry Pi Model 1B. This is one of the original Raspberry Pis. It is a 512 megabyte memory version, so it's the kind of version 2 of the original Pi 1B, but otherwise it's just the original one. Any Raspberry Pi would work for this task. Even the Pi Zero would work well for this. The processing that's involved here is almost nothing. In fact, the program sits there for most of every interval asleep. It does nothing for 59 seconds out of every 60. I have often had both the battery test program and the cave light testing program running at the same time, and they have no trouble whatever on this old Raspberry Pi. You could probably run several light tests and battery tests at the same time and have no trouble at all. So the Raspberry Pi is connected to a relay board and a 16-bit ADC, analog to digital controller. The ADC has a precision of, as you can see, 0.000125 volts and a range of 0 to 4.096. So for testing over 3.5 volts, I use a voltage divider. The 18650 batteries in an open circuit or a low current drain will run about 4.2 volts of open circuit voltage. And so I need to knock those down a little bit. I use the voltage divider on those. I also use the voltage divider, of course, for 12-volt lead-acid batteries. This presentation does not show what I've come up with for lead-acid battery testing. That's a completely different deal. But it does show other kinds, the 18650s and the dry cells. The test load is a pair of 30-watt, 15-ohm ceramic resistors. The resistors can make up 3 different loads by either using just one of the resistors, or by connecting the 2 in series, or by connecting the 2 in parallel. So here's a picture of the test rig. You can see the Raspberry Pi computer is in the upper left. Just below it is a breadboard. This is one of the pluggable module breadboards, very commonly used for all kinds of digital and electronic experimenting. The ADC board is in the middle, about in the center of that, and that particular ADC actually has 4 ADC channels on it. I only used one here, but it would be very simple if you wanted to rig multiple tests using different ADC channels. The relay board is wired up in such a way that it disconnects the battery under test from the load until you actually are ready to run the test. And when the test is done, when the battery reaches its discharge point, then the relay disconnects it from the load. I do that in order to prevent the batteries from being damaged by over discharge. I'll talk more about that later. This picture shows the test loads. It's kind of hard to distinguish them, but the 2 load resistors are on the left side of this cross made out of aluminum. The aluminum is there for heat sink. With the batteries I'm testing, describing in this presentation, heat is not an issue. But when I was running 12-volt lead acid batteries on it, those resistors would become fairly warm, and the aluminum stripes there help to dissipate the heat. They help to keep things down a little bit. The battery under test is in top center. You just use whatever kind of battery holder you want. And I made up several different voltage dividers. And this particular rig is not using one of them because it has a AA battery. The batteries that I used are for the 18650s. I used 3 different kinds. On the left is a Garbarial battery. This is a cheap piece of junk. It's rated for 5,000 milliamp hours. It's well, we'll see the results when we get there. The middle fire is also a cheap piece of junk. It is an ultrafire rated for 5,000 milliamp hours. The battery on the right I have labeled as the purple battery throughout this testing. It does not have a brand name on it. I bought this battery at 18650batterystore.com, and it is rated for 3350 milliamp hours. You will see when we get to the testing graphs that it actually delivers pretty close to that. In the AA size batteries, for nickel metal hydride, I used a Amazon Basics. These batteries are rated for 2400 milliamp hours. I used an Energizer rechargeable battery that's rated for 2200 milliamp hours, and an Eneloop battery which is rated for 2000 milliamp hours. Both the Eneloop and the Energizer batteries are well used. Those batteries are out of my personal stock, and they are 10 years old, maybe more. The Amazon Basics battery is fairly new. At the time of this testing, it was probably 6 months or so. So how do you compare the batteries? The ultimate measure of a battery is how long it will run its load. And for caving, of course, that usually means the headlight. Batteries are usually rated in milliamp hours, but that's not the same as either power or energy. As long as the voltage is the same, milliamp hours is a reasonable basis for comparison. But because the AA and the 18650 batteries operate at different voltages, the milliamp hour capacity ratings on them cannot be compared. They are not similar. So a better method of comparison is to use the watt-hour capacity. How many watt-hours can a battery deliver? The watt-hours are one common measure of energy delivered. I suppose I ought to digress here for just a moment. For those of you who are not well versed in electronics and electricity, the difference between power and energy is time. Power is an instantaneous measure of what a battery or a power source can deliver. Energy is that power delivered over time. So a watt is a measure of power. A watt hour is a measure of energy. The official metric unit is a joule, and 1 watt hour is 3600 joules. When you build battery packs using multiple batteries, the milliamp hour capacity of the pack depends on how they are connected. If wired in parallel, then the milliamp hour rating of each battery can be added to all the other batteries in the pack. So a parallel pack of two 2000 milliamp hour batteries produces 4000 milliamp hours as the rating. If you're wired in series, then the milliamp hour of the pack is the rating of one battery, assuming they're identical. If one of the batteries has less capacity than the others, then it becomes the limiting factor. So two 2000 milliamp hour AA batteries wired in series is still only 2000 milliamp hours. It has twice as much energy because there's two batteries, but it's the same milliamp hours. Watt hours can always be added whether in series or parallel, and the watt hours can always be compared regardless of the voltage or the pack configuration. So here's a couple of examples. The standard Stenlight power source is two 18650 batteries wired in series. It's rated for 2400 milliamps, but that's at 7.2 volts. So this is the same milliamp hour as one 18650 battery, but it's twice as much energy because you have two of them wired in series. The Princeton Tech Apex, a very common caving light, uses four AA batteries wired in series. So the milliamp hour rating of the pack is the same as one battery, but the pack will deliver 4 times as much energy as one battery because it has four of them. Milliamp hours versus discharge rate. The energy that a battery can deliver depends a lot on how fast it's discharged. If you discharge a battery rapidly, it won't deliver as much energy as if you discharge it very slowly. 18650 batteries in particular have a maximum discharge rating. When you look at 18650 batteries, besides the milliamp hour rating on them, one of the other characteristics you should look at is the discharge, the maximum discharge rate. Most 18650 batteries will run between 5 amps and 10 amps of maximum discharge rate. As a general rule, the higher the max discharge rate, the lower the energy capacity of the battery is. So a battery that can deliver 30 amps may only have 2000 milliamp hours of capacity. A battery that can deliver 4 amps at maximum discharge may have well over 3000 milliamp hours of capacity. For most of what we do in caving, the current drain is well under the lowest max discharge rate, and so you're really looking for a battery that has a low maximum discharge rate because it will deliver more energy to the lights and whatever other devices you're using it in. Almost all the 18650 batteries that you see on Amazon are cheap Chinese snake oil. As I said earlier, I have not ever found a truly good 18650 battery on Amazon, and I've searched all over the place. If you look for the common brand names, the good brand names, which are LG and Sanyo and Panasonic, you can look for them on Amazon, but you're not going to find batteries that truly are those brands. The high discharge, well, I mentioned that. You can also tell a fake battery by weighing it, and I've talked about that early on. In nickel metal hydride batteries, the snake oil is not nearly so much of a problem. The ratings on them are usually pretty close. Typically, a AA battery is rated for between 2000 and 2400 milliamp hours, and a AAA battery is rated around 700 to 750 milliamp hours. The good name brands that I mentioned there, Eveready, Sanyo, and Panasonic, are more consistent. Eneloop is a brand that used to be owned by Sanyo and is now owned by Panasonic. So the Eneloop batteries have a good reputation, and they have served me very well. Those are good batteries. Do not overcharge batteries, especially lithium ion. They can explode. Another of the things that you need to look for when you're buying lithium ion batteries is whether they have overcharge protection built into them. That's often abbreviated as just a protected battery. Most 18650s do not have protection in them. And in that case, you have to be very careful to use a smart battery charger, a charger that knows how to tell when the battery is full. In nickel metal hydride batteries, there's really not, the batteries never have any protection built into them. It depends entirely on the charger. And most nickel metal hydride battery chargers are pretty good about that. It's not usually an issue with those batteries. you do want to invest in a very good charger. Amazon has a lot of good ones, and as I note here, there are some that can charge both 18650 and nickel metal hydrides, and they'll auto detect whatever you drop in, it knows how to charge. In addition to overcharging, you can also damage a battery by over discharging it. That's particularly true of the of the lithium ions, but any battery will be damaged by over discharging. So for my testing, I ran the 18650s down to 3.1 volts. That's about 95% discharged. And on the nickel metal hydrides, I ran them down to 0.9 volts, which is also about 95% discharged. That's the reason why I put the relay in the circuit. When I start the testing program, the first thing it does is pull down the relay to connect the battery to the load. It then checks the voltage every time it goes around, at every regular interval, which in most cases for my testing was was 1 minute, 60 seconds. And once the voltage drops below a cutoff that I set, then it releases the relay, disconnects the battery from the load, and therefore prevents any kind of damage. All batteries have some small amount of leakage current, usually measured in picoamps, so it's very small. Good quality lithium-ion batteries will lose about 3% of their energy storage per month. Nickel metal hydrides rated for low discharge, such as the Eneloop, also lose about 3% per month. Some nickel metal hydrides can lose up to 30% of their energy capacity per month. So basically, you should top off your rechargeable batteries a day or two before any caving trip. So let's dig into the graphs here. This graph shows a garbarial versus a purple on a 15 ohm load. This is 18650 batteries. You can see that the voltage starts out more or less the same. The garbarial, which is rated at 5000 milliamp hours, only ran for a little over 200 minutes. The purple battery, rated for 3350 milliamp hours, ran for 740 plus minutes. That's 3 times as long, which is about what you'd expect. What it means is that the garbarial battery is delivering, even though it's rated for 5000 milliamp hours, it's delivering maybe 1000. Maybe 1000. It's snake oil. And if you look at it this way, in the milliamp hours delivered, you can see that they're delivering at about the same rate, but the garbarial delivered 909 milliamp hours and the purple battery delivered 2850. Just slightly more than 3 times what the garbarial delivered. I could probably have gotten a little bit more out of them if I had run them down to a lower voltage, but I didn't want to damage the batteries. In terms of watt hour delivered, this is the real measurement of the batteries. The garbarial battery delivered 3.2 watt hours and the purple battery delivered 10 watt hours, just about exactly 3 times as much. Looking at the AA batteries on the discharge voltage curve here, this battery has this graph has all 3 different kinds of nickel metal hydrides plus an alkaline dry cell. The milliamp hours actually delivered by the batteries are shown there in the legend on this chart. In the AAA voltages, comparing an alkaline to a nickel metal hydride, the alkaline battery started off with higher voltage, but it eventually crossed over the voltage. The nickel metal hydride had a flatter discharge curve, and that's fairly typical. The nickel metal hydrides will stay at a voltage longer than the dry cells. So comparing the delivered energy, this is probably the most important set of data that I collected. The lithium-ion purple battery delivered 10 watt hours. The garbarial delivered 3.2 watt hours, just about 1/3 as much. Interestingly enough, the nickel metal hydride AA battery delivered in the Eneloop delivered 2.3 watt hours, and in the Amazon battery is 2.6 watt hours. Part of that difference is because the Amazon battery has a higher rating, and part of that is because the Eneloop battery is 10 years old. A newer battery could probably have done somewhat better. But the interesting thing is that those batteries delivered almost as much power, almost as much energy as the cheap lithium-ion Garbarial battery, even though they're about 1/3 the volume. Both batteries delivered more power than the alkaline AA. The alkaline AA delivered about 2 watt hours. So in all cases, the nickel metal hydride battery delivered more power or more energy than the alkaline battery. And the same held true in the AAAs. The nickel metal hydride AAA delivered more energy than the alkaline AAA. In conclusion, for 18650 batteries, you want to shop very carefully. Like I said, and I'll repeat it again, most of the 18650 batteries that are out there are snake oil. If you're buying an 18650 battery that's includes a flashlight, it's probably snake oil. You want to go to probably a specialty seller such as 18650batterystore.com and to buy your batteries. Rechargeable nickel metal hydrides deliver more energy than alkaline batteries, and a set of 4 nickel metal hydride AA's will deliver about the same energy as a single good lithium-ion 18650. And so let me put this in the form of a light test using a Princeton Tech Apex with nickel metal hydride batteries in the spotlight mode. You can see that the nickel metal hydrides in high ran the light for just a little over 2 hours, and in low they ran it for roughly 500 minutes, about 3 times as long. So thank you much for all of this. There is all of the data and this slideshow are available online. I believe that the URL for that site is in the abstract, and I will also put it in a title overlay here at the end. So thank you very much for your attention, and have a good day. Enjoy your convention.